Lab 5, double pendulum motion. This experiment demonstrates how small changes in initial conditions produce dramatically different outcomes in a chaotic system. We will observe two identical double pendulums that differ by only 15 degrees in their initial angle. I changed it from 0.1 degree because the differences weren't as obvious initially. Double pendulum is one of the simplest chaotic systems. Unlike a simple pendulum, which swings periodically, a double pendulum can behave unpredictably. Basically, their motion cannot be predicted far into the future, or it's very difficult to do so. Key question: how can a 15-degree difference cause completely different motion patterns? Our expected outcome is that initially both pendulums swing nearly identically. However, within seconds, their motions diverge exponentially. This demonstrates sensitive dependence on initial conditions known as the butterfly effect. All right, theoretical background. A double pendulum has two rigid rods connected end to end with masses of the joints. Let theta 1 be the angle from the first rod from the vertical, and theta 2 be the angle of the second rod. The system follows coupled nonlinear differential equations. This is basically it. It's pretty straightforward. The key feature is nonlinearity. These two terms, the sine theta and the sine theta 1 minus theta 2, cannot be simplified for large angles. These create strong coupling between angles, producing complex, unpredictable behavior. Experimental setup and procedure. So we set the length to 1.5 meter, the mass to 1 kilogram, and then the initial angles to 30 degrees and 45 degrees respectively. These are just a bunch of smaller implementation details over here. And then this is the video. I don't think I can put it side by side, but I'll put it later. Watch the two lower masses as time progress. Initially, they move nearly in sync. Their colored trails almost completely overlap at t equals 0 seconds. As time increases, the trails separate visibly. By t equals 10 seconds, the masses occupy different regions of space and move independently. So our observations. The early phase, for the first 3 seconds, the two pendulums were pretty similar. After I changed it to like 45 degrees, the early phase was much shorter, but the difference is still pretty crazy. And then the late phase, the pendulums behave basically completely independently. The lower masses are in two totally different spots. So analysis, separation distance grows as delta dt approximately equals delta ds times e to the lambda t, where lambda equals 0.15 seconds, or I guess 1 over seconds inverse. So our delta d sub s equals 0.0003 meters. We predict delta d of 10 is around 0.3 meters. This matches our data perfectly. And then, the rest is pretty, it checks out as well, basically. Discussion and physical interpretation. Why chaos occurs? The double pendulum has 4 degrees of freedom in phase space. Nonlinear coupling allows orbits to explore the space in complex, non-repeating patterns. Simple pendulums with fewer degrees of freedom cannot be chaotic. Conclusion and summary. Primary results. Two double pendulums differing by 15 degrees diverge exponentially over 10 seconds. Separation distance grows by a factor of around 1,000 times, from 0.0003 meters to 0.3 meters. Growth rate matches exponential model with lambda equals 0.15 seconds. System is deterministic but unpredictable due to exponential uncertainty growth. That's about it. Thank you.